Okay, welcome to our session today. Yeah, today I think we're going to take we're going to give some comments on probability and decision trees, and I think then I want to show you the plan for the rest of the semester, which we don't have too many classes left, and also a bit about the exercise. Okay, but let's first cover just this decision tree, and then we discuss a bit about the plan for the future. Okay. Yeah, so just to see what we were doing, I think we were spending quite a lot of time on this probability quantification, but the main thing was that you have some process that depends on some input, and that input doesn't have just one value but has a distribution, right? How do I get that distribution? It's depends on each case. I might not know anything, I might know a little bit, but it can be a lot of speculation, and that's sometimes where the part of the expert comes into play. Okay, if you have an expert, you have a consultant, you have someone senior in the company, they have experience from before, so they can really help you to shape these distributions in a better way, or they can help you also to get information to shape those distributions in a better way. But we said we looked at two methods. One of them was Monte Carlo. I took a random sampling, okay, and we did this exercise in Excel in class. Then I told you we did it also in Python, which I think is the method that you should use. Okay, it's the tool that you should use, because in Excel really you are a bit limited with the number of iterations you can make. Okay, while here you can see really the effect of increasing to really high numbers and see what effect does it have on the results. Okay, so we did it in Python, and then after that we talked about Latin hypercube sampling, which I told you is simply a better way to make more even sampling. Okay, Monte Carlo is by its nature is random, so I don't have this. Here I'm trying to divide in blocks the CDF and then try to sample randomly from each block. Okay, and you see we got similar results. So I told you you should try to reproduce using this code, what I have done in class. And then the last part about probability was decision trees, and that's what people were using in the 70s, 60s. They didn't have Excel, they didn't have computational power to do many simulations, so they simply used decision trees. Okay. And decision trees, they are typically based, or they typically work very well to include discrete decision variables that are either one or the other. Okay, for Monte Carlo, for Latin hypercube, we usually have something that we can sample continuously. Okay, like here I gave you an example. We can decide to abandon the field, to abandon the development, or to develop it. Okay, that is a square. That's how I make a decision node. I can make it bigger. Okay. Then I have another decision, which it could be different to code that decision in a continuous, in Monte Carlo Latin hypercube. Okay, but then I come to something that has to do with chance. Okay, for example, the price of oil, then the size of the development. Okay, these are chance nodes. Okay, and like I told you, this n, they are just they're not, it's not something I decide, it's something simply I get. Okay, but I told you that this n is interesting because this n is representing the distribution we calculated before. Okay, like that continuous distribution, that continuous log normal distribution, these three branches, okay, that's what we call a branch, okay, are kind of representing the whole distribution we showed before. Okay, which is a bit strange. You say, well, we were struggling quite hard to get this continuous distribution, this nice shape, and now you came and killed it just with 3 branches. Okay, how come? So, but that's really decision trees. I cannot have infinite number of possibilities, because remember, here I have to make the computation of each option. Here I have 3 here I have 3, and here I have 3. Okay, so how much is that? 27. Okay, so I have to calculate 27 cases. If I include here like 10 cases, then I will have 10 times 3 times 3. The size is growing exponentially. Okay, also with this price, if I put 10 and 10, then it grows, it explodes, depending how many layers I have on the tree. Okay, so I told you, like, for example, what a way to do it in Excel will be to write all cases. Here I have just 9, and it should have 27. Okay, so that's only for one FPSO, only for different prices and for different ends. Okay, for the high price, the 3 ends; for the medium price, the 3 ends; and for the low price, the 3 ends. After I have this, I, for example, can calculate the value of each option, which, for example, the n, you got okay, like what you get, I think this is the last exercise of exercise set 1. Okay, you have an expression which is a bit like that. Okay, for early field development, they recommended using that expression, and I can calculate, if I have the price, I have the NP, and I have the cost, for example, I can calculate the NPV. Okay, so I can assign to each branch, okay, to each, not branch, but to each path. Okay, this is a path. I go develop, FPSO, high price, and then N, for example, which is high. Okay, I should go copy and paste this many times. Okay, has to be at the end of each branch. Okay, but I can calculate the value. But more importantly, in a tree, you always have to remember there is a probability associated with each path. Okay, always. Okay, that probability, you find it by multiplying. For example, here I told you this is a decision node, really doesn't have a probability of occurrence. It's simply something I decide. Okay, either black or white. Okay, but on these ones I have a probability associated. I have to assign, and the sum has to be equal to 1. Okay, so for example, I have some probability, and this is where the expert comes. They say, well, there is a 40% chance that it will be low now in the future, or there is a 10% chance that it will skyrocket, something will happen, or there will be 50% probability that it will be at 70. Okay, an average at 70 value. Okay, the sum of all of these guys, probability in one given layer of the tree, has to be equal to 1. Okay, and then the probability will simply be probability of this times the probability of the other one. So let's just repeat that. Okay, just start to write. Okay, so for example, you have to develop, okay, to abandon, okay, and that will be the end of the branch, which we make with this triangle. Okay, and then we had another decision, which was FPSO was subsea, was it? Jacket, TLP. And after that I had the chance node, which was price, oil, high, low and medium, again high, low and medium, high, low and medium, price of oil. And then here I had the N, okay, the layer of initial in place, where I have again price, low and medium, and that will be the end of the branch, the end of the path. Okay, it's getting messy. You make it nicer in your notes, please. You don't have to copy. My mistakes. Okay, we usually don't make the just, I think it's important to make it at least a few times to see how it expands, okay, such that you understand how the tree looks like. But after that, you don't really have to make the tree, because you know more or less how it looks like. Okay, but I think it's important you draw it at least once to be sure that you understand how it looks like. Yeah, and this first one was price, was FPSO, jacket, and this was TLP because I can decide, right? But then I have here, this will be the price 1, price 2, price 3, and then here also the same thing with price. Just make it into another color. Okay. And here I have the ends, okay, for each one of these. So I have N1, N2, N3, and the same thing here, N1, N2. Okay, so you see that for that is what I called this is what I call the layer of the tree. That's a layer. Okay. Also the same thing with the price, that's another layer. Okay, to go all the way down here. Okay. That's the layer of the offshore structure, that is the layer of the price. Okay, and then you have a layer of N, okay, because and what I call the path is actually this guy. From here, well, I decided to go to FPSO, then for one chance I had this price, and then I had this N. Okay, this is what I call a path. Okay, so each path has, so let's write it here, each path has an economic value, for example, okay, and a probability, okay, which is the sum of each layer from layer equal 1 to n of the probability of I No, that's not that's not right. Simply the multiplication of all probabilities, okay, for all layers. I forgot how to write it. Any mathematician that can come to my help? How do you write if it's a not you want to multiply the probability of this one, which is, we know it doesn't have, it's just simply 1. This will be also 1, but then I have to multiply probability of this layer and the probability of this layer. So it's like a compound probability. How do I write it in a nice mathematical way? Okay, well, defeat. So we probability of, for example, of path will be probability of the PO that you are going times the probability of n. Okay, but if you have more layers, then you have to multiply the probability of each layer. Okay, so each path not only has a value, okay, like we know, like it's sort of a Monte Carlo in a way. Okay, I choose a value of PO and I choose a value of n, but also has a probability associated with that path. So keep that in mind always. Don't forget, in a tree, each one has also one probability. Okay? For example, let's make an example. Let's solve the previous problem. Okay? That was TRR, okay, has a function of rock volume, net to gross, saturation of oil, porosity, recovery factor divided by BO, right? Using probability trees. probability. Okay, how would you solve it? Do I have any decision variable in that problem? Do I have to decide anything? Not really, right? Simply have all of them are chances. Okay, I have a chance for BR, a chance for net to gross, a chance for, I have all our chance nodes. Okay, so my tree will look like, and here, how many, first we have also to decide how do we want to discretize all of them, VR, NTG, SO, how many values are we going to use? Let's say we were using before 3, right? So let's use 3 also. So we have 3 for BR, okay? And that's how I make the tree compact, okay? I make it like that. Net to gross. Then I write 3 more SO. Then I have 3 more, and that will be porosity. And then I have 3 more, which I have FR, and I have 3 more, which are BO, and then finally I have DN. Okay. So see, if you imagine that, that will be a huge, large tree. Okay, how many branches do I have, or how many paths do I have? 3 times 3 times 3 times 3 times 3 times 3. Okay, how much is that? 3 to the 6. Seven. $729. Okay, I have 729 paths that I have to explore on that tree. Okay, now that's one thing. So how do I decide? So how do I get these 3? I know that you know that, for example, BR, right, looked like I think BR was a uniform distribution, right? So I have a minimum and a maximum. Yeah, I don't remember. I think they were 5,000, I think, barrels, and this was 6 to 50 barrels. Okay. So how do I get from this distribution, okay, which is continuous, to put it on the tree? I have to convert it to this thing, okay, to VR1, VR2, VR3, and then a probability associated to each one of them, right? That's what I need to put it in the tree. I have to convert from continuous to discrete. How do I do it? You know?
Instead of having continuous distribution, we can select for some intervals, and then for them we can define probability.
There are many methods, okay? So I'm going just to show you just a few. What Arpita said is one of the methods. Okay, so you simply define, one option is, and it's called, so let's say there are many methods, and here in this course we have worked with 2 methods. Okay, one of them, for example, is value discretization, in which the first step is I define arbitrarily, okay, in a way arbitrarily, values of the variable, okay, and values of the variable. Okay. So let's say I have my continuous distribution, okay, of BR, and then I say simply, well, I want this guy VR1 maybe equally spaced VR2 and VR3. Okay. I define those three values. I can make it equally spaced, I can make it uniform, but I define arbitrarily n values of the variable. Okay. Usually they are uniformly spaced. Okay. Step B is to read from the PDF, okay, the probability distribution function, its associated probability. Okay, so here I have the PDF, right? It was uniform, so I go and read, and all of them have actually the same, right? The same P1, P2, and P3. Okay? That will be P1, P2, and P3. Now, those three numbers, remember, for a layer they have to sum up to 1. Okay? That is the premise of the tree, that in one layer the three have to be equal to 1. Here they're not going to be equal to 1, right? Let's calculate, for example, what value do we have here. If we have, remember the area, okay, what we said about uniform distribution, if you remember, was a bit long time ago, but we say that it goes from a minimum to a maximum, right? And that the area under the curve has to be equal to what? To 1, right? So in this case we can say simply that the probability times max minus min, right, should be equal to 1, right? So for this particular case, the probability will be 1 divided by 6250 minus 5000. How much is that? Okay, 8 to the minus 4. Okay. Okay, so that's the number. When I read here, those are the numbers that I'm going to get. 8 e to the minus 4. But the sum has to be equal to 1. Okay, so the next step is to normalize the probability. Okay, that means I find a new P1 that will be the same step, okay, the same C, will be P1 old, okay, divided by the sum of all Pi's, okay? So that means 8 e to the minus 4 divided by 3 times 8 e to the minus 4, and that's how much it is? 1/3, okay, which 1/3 is 0.333. Okay, it will be P1, P2 will now be 0.333, and then P3 will be 0.333. Okay, so in this case, which makes sense, I made 3 samples, okay, and the 3 have all the same probability, 33.333%. Okay, now what would have happened if now I tried to sample from, for example, a triangle distribution, okay, which the triangle was like that, okay, and I have 3 values here: rock volume 1, rock volume 2, rock volume 3, for example. Let me make it just below to avoid confusion. What if the distribution was not normal, was not uniform. Okay. Okay, now the PDF is like that, right? I define 3 values, follow again the same steps, define arbitrarily n values, maybe they are equally spaced, okay, VR, V2, V3. Then I read the probability, that means I go up here and I read this number, and this number, and then I normalize, the same thing, right? But now the 3 won't have the same probability, okay, they are going to have different. Can I apply this method to discretize, for example, our CDF of, for example, our N, okay, PDF, okay, if you remember, or NPU, I think, okay, was not N, was NPU. We got something like that, right? Okay, can we use this method to discretize this distribution? Yes, right? It's the same. I define 3 values, NPU1, NPU2, NPU3, and then I read the probability and then simply normalize it. Okay? It's exactly the same. So this method that I use here to discretize this distribution, I can use it for discretize any distribution in n number of options. Okay? And it's called value discretization. Okay, and after I repeat that, in this case, this problem, all of them are going to, because all of them are uniform except for this guy, okay? I think this guy was not uniform, this guy was triangle, okay? Not uniform. But for all the rest, all the probabilities of each option, of each branch, okay, is going to be the same. Because this was uniform, this was uniform, 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 uniform. The only thing that is going to change is, of course, the value of the all the 3 options, okay? Because porosity is between a certain range, BO is in a certain range, and so forth. What do I do next if I have all of these values, right? Okay, let's make it, I think we have to make the notes nicer, so we can also apply this method. To discretize our NPU PDF, okay? And that's how, if you go back to our original example, that's how you get these 3 values, okay? That's how you get these 3 values and the probability. Okay, what is the next step? So how do I solve these 3, okay? How to solve the 3. Okay, the 3, if we remember, let's write it back once more. We have rock volume, we had was net to gross, then we had saturation, then we have porosity, then we had recovery factor, and then we had BO. Okay, I have to make combinations of everything against everything. So if I do it in an Excel sheet, okay, I have to make BR net to gross, SO, phi, FR, BO, and finally here I calculate the NPU. Okay, that will be my result. Here I write case, or maybe write case or path. Okay, NPU and probability associated with that case. Okay, so this will be, for example, BR1, NTG1, SO1, phi1, FR1 and BO1. Okay? With all of that input, you calculate NPU. Okay? Then you change. Case number 2, VR1, NTG1, SO1, Phi1, FR1, BO2. Okay? And then 3, VR1, net to gross 1, SO1, Phi1, FR1, BO3. Now you finished with the branch of BO, okay, for that particular line. Now you move to the next one, which is VR1, NTG1, SO1, Phi1, FR2, okay, BO1. 5, 6, VR1, net to gross 1, SO1, Phi1, FR2, still BO1, BO2, okay, VR1, net to gross 1, SO1, Phi1, FR2, BO3, okay, and so forth. Repeat 729 times, okay. For this particular case, if all of them are uniform, what will be the probability of each case? The same, right? If all probabilities, input probabilities, are uniform, then the probability of each case of each, we call it case or path, okay, is the same. Now I say, what if all of them are the same but they are triangular, for example? Will they have the same probability? They are not uniform, but now they are triangular, but all of them are triangular. Will they have the same probability?
Depends on the initial and final.
Depends on the initial values, right? Because if you have all of them are triangular, right? But then I chose to have these 3 for one variable, okay? But then I chose to have for the other variable, I chose to have maybe these 3, 1, 2, 3, closer to the peak. Okay, so we are going to get, in principle, different probabilities. Okay, even though it's the same distribution, depends depends on step, on this step. Okay, step A. Okay, it's only when they are uniform that you know they are all the same. Okay, now how do I digest it? And now I have 7 and 29 cases. I have NPU, probability. How do I digest that information? Remember, before, when we did our Monte Carlo, okay, with 1,000 iterations, right, what we found for NPU was this thing, okay, with Monte Carlo, or Latin Hypercube Sampling. We found something like that, and we found also that is the PDF and the CDF. We found something like this, right? What happens with decision trees? Okay, how do we get that with decision tree? We're going to take a break soon, so hold on. Don't despair just yet. One way, I tell you one way I like to do it, okay, which I think is a bit easier to understand. You take these results, right? These two, okay, let's call it column A and column B. So I say here, if there are many paths on the tree, okay, only if there are many, okay? Then I take column A and B, okay, NPU, and the probability of each NPU, okay, that will be column A, and column B. That will be step 1. Okay, we are taking today. Step 2, I'm going to sort column A from minimum, for example, to maximum. Okay, sort column A. Okay, and the probability will change. Okay, the position, for example, if now you have the minimum was here with each probability, now these two are going to be moved to the first place. Okay, sort, so it will say sort values using column A. Using column A. Then I have the probability what I can calculate here now is this cumulative probability. Okay, for the first one will simply be the first one. Okay, for the second one it will be, let's use different colors here, I think, otherwise it's going to get messy. Okay, here we have this guy. Okay, the green one will be the blue one plus this guy, okay, and so forth. So you can find from, because you have the probability only of each path, okay, but each path is now ordered. So if I sum these two that are one next to the other, okay, I say now the probability of having at least that value is this much, just the sum of this plus the other one. Okay, now if I go now below here, which is a number which is higher, even higher, I say the probability of having this number or higher is this one plus this one plus this one. Okay, and just the same thing, and then at the end again end up here, the probability of having something is below, right? No, it's not above, it's below. Below this number, below this highest number is simply 1, the sum of all of them, right? Okay, that more or less clear? Is if I have enough results, okay? If many paths on the tree, if not enough cases, I just report the NPU, okay, the NPU, okay, versus probability, and then based on that I take my decision. Okay, I can use that actually. Have, well, the reserve can be small and that has a probability of 20, can be very high has a probability of 30, and is in between it has a probability of something. Okay, I just report all discrete cases. Cumulative probability, and here I can calculate finally NPU so from the tree, depending how many branches, depending how many cases, you can actually get the same result as Monte Carlo or LHS. Okay. Okay, but if you have enough values, if you don't have enough, then simply just report all these discrete cases. Okay. Now, before we take a break, I have to say there are other methods to discretize distributions, continuous distributions. Okay. Okay, the one that we saw now was value discretization. In one exam, previous exam that we had was actually, it's another method to discretize. Okay, and the instructions were given in the exam how to discretize it. Okay, but basically the method is, I have to check the name of this method, but it's, for example, on the CDF, okay, let's say, for example, you have a distribution like that. Okay, this is 0 to 1. So simply you define the number of probabilities you want and the value. Okay, for example, you want the first probability to be, I don't know, 20-30%. You define that number and you put the lower there. For example, you say you want 3, okay, 3 points, P2 and P3. Okay, so you move actually this up and down depending how much do you want. If you want them equally spaced, that's fine. You can have one, the two smallest, and the one in the center bigger. That's something you define. Okay, then you draw horizontal, so you should be horizontal lines. Okay. Then you define this endpoint here. That will be for each interval. And now you want to find, because now you start from the opposite way, right? You start the probabilities and you want to get the value. Okay? To find the value, you have to find a vertical line in which these two areas are the same. Okay, for example, here it will be here, that will be the value 3. Okay, then you do the same here. This will be the value 2, and then you do the same here. Okay, here it's slightly bad. It should be, the two areas should be the same. The value 1. Okay, so is change the location of value 1, value 2, and value 3 until areas are the same. Yeah, and the areas that I'm referring to are this area and this area. Okay. Okay. Another method. Don't sweat it too much. There are many methods to discretize distribution. Okay. Value discretization, this guy that you start with probability, and each one is like, each person has his own preference. Okay. Some people like to drink orange juice, some people like to drink apple juice, and some people say, well, this one is better than the other because this one has vitamins. Okay, no, this one has, they like it because of some reason. Okay, so that's exactly, and that actually was given in the exam, and this instruction was given also in the exam, that these two areas have to be actually the same. Okay, and that's how you get the probability is the distance between these two. Okay, and the value is actually this guy. Okay, and that's the discrete probability. So the discrete distribution is value 1, P1, value 2, P2, and value 3, P3. But in this case, I started differently. Okay, I just set the probability. And that is very good if you want to set the probability. You want that, you know that you want, because what could happen if your distribution, you don't know exactly how it looks like. Okay, it might be that if you do this sampling using this method, you might end up to have one with only 5%, another with 5%, and then the one in the center has 90%. Okay, which is not fair. Okay, you are taking three options. In one of them, the probability is very high. Okay. By using this method, you are forcing it to be equal, and then you're finding the value that it's. Let me see. I took some slides from another course. So if you want to. If you want to learn more about decision tree, uncertainty quantification, I really recommend you to take a course called Subsurface Decision Analysis. Okay, it's taught by a professor that is an expert in this area called Reidar Bratvold. Okay, they have it here at NTNU. I'm not sure if they still teach it. They should, I guess. And here they talk about more in detail these methods. How do you quantify uncertainty, and then how do you make decisions based on all of this uncertainty, right? So if you want to know more, I really suggest you to take that course. Okay, I'm going to put it here. It's called Uncertainty Quantification. Okay, Monte Carlo simulation. Also, you want to work a bit more with decision trees. Okay, take the course, because then we have to make decisions. Okay, and then it's not so trivial. For example, if I come to my manager saying, well, that's what I found. Okay, let's say I didn't do this 720, but then I have just these 3 cases, okay, or 4 cases. How do I decide? Okay, do I prefer to take the one average? Do I prefer to have the high gain but high risk that has low probability? So those things are studied in this course. Okay, subsurface decision analysis, because then we have to take decisions, and then we have to take into account what happens in the brain when we take decisions. Okay, and that method is called, this method here, I'm not sure if this guy mentions it. Yeah, I was going to show you some slides from this course. Okay, that's this professor Bratvold, and he has a whole part how to discretize distributions. Okay, so for example, you have all of these methods. So if you want only 3 points, 3 value, they say, well, you can use these 3 methods. You have this momentum matching. I think that's we'll see. So if you use these methods, simply you take the P5, P50, P95, and that is fixed, the probability you used. Okay, but if you use the McNamee-Celona, then you have another P50 and another percentage you use. Okay, now if you want to use more than 3 points, okay, that's an example. You want to use more than 3 points. Okay, that's our bracket median and bracket mean. Okay, that's I think the one we are using is bracket mean. Okay, exactly the same, trying to find that the 2 areas are the same, and you can do that by an integral. Okay, and here is this value discretization. Okay, so I'm not going to copy this material because it's not mine. Okay, but just be aware, that we have all of these methods maybe we just copy this slide, okay? The one with all the methods. And if you're interested, if you have to use it in your project, if you have to use later in life, just you know what options do you have. Okay, and this is from Professor Radar Bradbold and Aoji Hong, I think is his last name, but I forgot how to write Aoji Hong. Okay, but there are many methods, many choices, so you decide which one you use next. I think the one we have covered here are this value discretization, and we have covered this mean, okay, bracket mean. Then instead of doing graphically, there is an equation for using the integral, okay, because basically when you're integrating these two areas, they have to be the same, okay. So you have to converge this value until this integral on this side and the integral on that side, they are the same. Okay, now let's take a break. Okay, do you have any question before you go to a break? No? Yes?
So we just use our eyes and say, I think this area is the same?
Yeah. For this course, yes. Okay, and actually the author here, in these instructions I gave you, he argues that the naked eye, okay, is actually quite good. Okay, I think he mentions it someplace here. The eye is surprisingly good at doing this. Okay, we had one group a few years back. They were very skeptical. They say the eye is not good, and they did it analytically. Okay, and finally they were a bit disappointed. They got the same result that the other groups. Okay, but if you want to try, also you can try. Okay, or you can use the first method we saw, which is also quite okay. Okay, you define 3 values, read the probability, and you normalize. Okay, it's called value discretization. Let's take a break. That's really a bad. But well, we really just make the plan, and so for those of you who missed our so we just said solving the exercise, the TRR problem with the probability tree in Python. I just gave a description of the code, and then the results, and then we were making some plan about the remaining topics, and a tentative teaching schedule, and I was saying that the exercise 2 will be probably merged with exercise set 1 and delivery date after Easter, but that doesn't mean you have to keep working on it. Okay. And probably for this exercise set, we will have exercise set 2. There will be one exercise using LedaFlow. Okay? Clear? Do you agree with the program? Yeah? Okay. Now, one thing before we close now, we didn't have time, we continue with offshore structures on Friday, but one thing was a clarification, I think it's important to mention here, was on problem set 1, problem 6, okay. If you remember, so to calculate the NPV of the revenue only, right? That will be the sum of how much was produced in a given year, okay, delta QP I, multiplied by the price, if we assume a constant oil price, divided 1 plus I to the power of, yeah, that's not a good, let's call it discount factor, to the power of I, from I equal to 1 to the number of years. Okay, so if you, that's how you calculate just the part on revenue, right? So here we have year 1, 2, 3, 4, okay, that's years, and that is production. Okay, for example, if you decide to produce like that and then down, okay, what you have to make is for each year, okay, this production, that's your delta NP for 1, okay, and the same thing for 3. Okay, so what you're doing basically, that expression tells you is delta NP1 times price of oil divided by 1 plus discount factor to the power of 1 plus delta NP2 price of oil divided by 1 plus discount factor to the power of 2 plus delta NP3 NP3 PO 1 plus discount factor to the power of 3. Okay. Okay, that's how you actually compute it. Okay, what we are doing here is saying, well, that can be represented also as NPU, the total that I produce cumulative, right, times the price times this discount factor. That's what we are doing in our exercise. Okay, we are representing, instead of doing this complicated calculation, okay, because I have to assume a production profile, I'm saying I'm going to approximate all of these, because the sum of all of these guys is delta PU, right? NPU is actually the sum, and I don't learn, I always want to write it here. Delta PU is the sum of delta NPI from I equal 1 to n. Okay, so I say that's a way to represent the revenue, okay, the discounted revenue. Now, this factor, some of you have been asking what this factor depends on, right? What number should I assume? Well, first note that it depends on this number, the discount factor. Okay, if I have, depends also if I have 7%, 12, if I have 5%, okay, will change that factor. Also depends how many years you are considering. Okay, it's not the same to take 20, to take 15, but also depends on my production profile. Okay, if I have a very long plateau, okay, if I have a very long plateau and then decline, if I have a very short plateau and then decline, this will affect that FD factor. Okay, so what I say in the exercise, look at the snow white, because you already have this data for the snow white. Okay, you have this guy to the right, and then you can simply have how much you recover, the price of gas, and then calculate that discount factor for all the cases that you made. Okay, and you can see what is the range of this FD, and that is the range that I suggest you use in this exercise. Okay, because you have data, so you can look at that data to see how the discount factor looks like. Okay, and some of you say very correctly something between, at least the numbers you're getting is something between 0.2 and 0.4. Okay, or 0.6, 0.2 and 0.6. Okay, but you have to make the homework. You have to look at the data you have at least for the snow white case, and then see, you know, what is that factor. Okay, that's now we run out of time for today. Any questions before we close? No? Okay, see you on Friday. Have a nice week. Thank you for showing up, 8 in the morning.